Hi, so I'm going to show you how to set up your COMSOL model to run a two-cylinder configuration for a flow past the two-cylinder configuration for high Reynolds numbers of 7,000. So let me first show you a picture of what the geometry of the problem is going to look like. It's going to be a 25 diameter wide domain with a 17 diameter tall inlet condition. And then the center of the cylinder is going to be placed 5 diameters away, plus the length between the two cylinders. And we say that the length between these two cylinders is going to be capital L. And we have the larger diameter, which is at the origin, is going to be capital D. And the smaller diameter, which is going to be at some length away from the origin, is going to be lowercase d. Now, the angle created between the axis from the center of these two cylinders and the free stream velocity is going to be alpha. So let's go ahead and go to remote desktop. Okay, now we're going to open up COMSOL. Okay, now that we have COMSOL up, we're going to go to the model wizard, 2D, and fluid flow, single phase flow, turbulent flow, and K epsilon. So we're going to add that. Now go to study, time dependent, it's done. Okay, so let's go to our parameters. We'll call this one geometry. And the first variable we're going to make is capital D. And we're going to make that 0.1. And we're going to put some units here. So we're going to say meters. Now we're going to say our width is 25 times D. Our height is 17 times D. And our CX, which is the placement of the inlet, is going to be 5 times D plus L. So later on, we're going to define L. So let's make a new parameter list and call it second cylinder. So we're going to say that we're going to have a D ratio. And for now, we're going to keep it as 1. And we're going to say our small diameter will be the larger diameter times this D ratio. And then we're going to say L star, or the L ratio, is going to be 2. And that makes our length equal to the length ratio times the diameter. We're going to have a separation distance of 0.2. Now we're also going to define alpha. This is going to be 30 degrees. And finally, we're going to do D average, which is going to be the sum of these two. And then we're going to divide 2. Okay. So when we go back to original parameter, we have 5 times D plus L. That's no longer in red. Now let's go back to the second cylinder here. Okay. We're going to create a new parameter right here for the flow. We're going to say the Reynolds is going to be 7,000. I'm going to say the density is going to be 1,000 kilograms per meter cubed. Okay. And our viscosity is going to be 1 e to the minus 3 Pascal seconds. Now our flow speed is going to be our Reynolds times mu divided by rho times T average. Next parameters we're going to define are time step. For this, we're going to make an over prediction in the Struhal. So we're going to guess 0.5 for the Struhal. And then we're going to say our shedding frequency guess. It's going to be the Struhal guess times U over D average. And our shedding period is going to be 1 over F, yes. Now we're going to define this variable n, which we're going to take to be 10. And then we're going to say that our delta t, for our time step, is going to be t guess over 10. So next, we're going to say how many time steps we're going to have. So we're going to have 100. And that'll make our final time equal to delta t times the number of time steps. And next, let's define a boundary layer. So boundary layer thickness is going to be 0.1 times D average. We'll just use capital D. D over the square root of Reynolds. And so it's 1/10 of the viscous sublayer. We'll use that later on. Okay, next we define a step function, which will ramp up the flow coming towards the cylinders. If we plot it, we see that the step function gets to a stable value at around 0.25. So we have to go back and we're going to add another parameter, which is going to be start time. And this is going to be the width divided by velocity. So we're going to start our simulations once the entire computational domain has the same fluid velocity. We'll add 0.25 because that's that ramp up time. All right. So now let's go to geometry. Go to geometry, and we're going to create the rectangle first. So we'll put width here, height there. And now we're going to do negative cx, the x position, negative h over 2. And we'll build all that. Okay. Now let's make our first circle, or our cylinder. Now the radius is going to be capital D over 2. It's going to be at 0, 0. Build all objects. Now let's see if we can make another circle. It's going to be lowercase d over 2. And then this is going to be L times cosine alpha. And the y is going to be L times sine alpha. Now let's build all the objects. Okay, so the next step, we're going to do a Boolean operation to subtract the two cylinders. So the objects to add is going to be the rectangle, and to subtract are these two cylinders. Now we'll go to our material, and insert a blank material. And for the density, we'll say rho. And for the viscosity, we'll put mu. Now, in the turbulent flow, we're going to make a wall condition here. We're going to make the top and the bottom walls a slip condition. This will allow for a bulk flow going past the cylinder. We can also create the inlet. This will be our inlet. And we're going to say that it's going to be U times step 1 T 1 over seconds. And then we're going to create our outlet. So here's our outlet. We're all set there. Now let's go to our mesh. We are going to do extra fine. We'll build that mesh. And then we're going to do user controlled. And we will go down to, let's see, size 1 is extremely fine. And size is extra fine. Now we'll go to boundary layers. Boundary layer properties. And we will assign the first layer thickness to be ELT. That's the boundary layer thickness that we want to resolve. Now we're going to right click on study 1. Go to show default solver. And we're going to scroll down. We're going to expand this tab, that tab. Go to time dependent. And for time stepping, instead of free, we're going to choose intermediate. And that means that we are going to choose time steps. The solver is going to choose time steps between what we select as our output time step. And now let's define our output time step. We'll say range 0, 0.2, time st minus 0.2, and then we'll do range time st, and we'll do delta t, we'll do time st plus fin. That defines our output time step. Now we're going to go to study right here, and instead of generating the default plots, we're going to unclick that right here. And we're going to go down to results. And right click results, 2D plot group. Right click 2D plot group. Go to surface. And we're going to choose weighted classic. Go to range, manual range. Pick one. And now let's go to the expression. We're going to make the expression a vorticity plot. We're going to make this into a vorticity plot. Let's grab the vorticity in the z direction, multiply by the d average, and I divide by the velocity. So this should give you a non-dimensional vorticity that can be plotted from -1 to 1. Step plot with 1. Step 1. Okay. Perfect. Now let's save this model. Make a new folder. We're going to call this base model. Let's see. Now, let's save this again as a Reynolds 7000. Now, just to give you an idea of how fast this takes to run, I'm going to go ahead and run it. So hit compute. Okay, so it finished. Here's the vorticity plot. Let's see how long it took. It took 4 minutes and 29 seconds. This is the non-dimensional vorticity plot. You see when there's a small gap between these two cylinders, the fluid's able to accelerate between the gap and create these large swollen vortices. So this can also be done for a parametric variable. So if you want to make a parametric sweep, you would right-click on study. You'd go to parametric sweep, and you could change one of the variables, such as the diameter ratio, the length ratio, or the alpha. Let me go ahead and save this. And I can show you how to run it for a parametric study. So let me go ahead and open up a new COMSOL tab. Okay, we're going to go ahead to open. And we'll go to where we saved our file. We're going to open the base model. And we'll save this. We'll call it Reynolds 1000 sweep. Now we'll right click on study, parametric sweep. We're going to add 3 variables here. 3 variables are going to be, what's down first? It's going to be the alpha, yeah, alpha's fine. Diameter ratio and the length ratio. Let me get rid of the diameter ratio. Go ahead, delete that one. So for now, we're just going to look at alpha and L star. So let me put this in terms of degrees. We're going to do range, 0, and steps of 15. Range. Sorry. Range from 0 steps 15 all the way to 180. Okay. Now for the length ratio, we'll do range. We'll do 1.1 all the way in steps of, actually, let me write them all out. We'll do 1.1, 1.5, then we'll do range, 1.5, steps of 0.5, all the way to 4.5. Now let's save this. And we'll go ahead and compute. And instead of specified combinations, we'll do all combinations. And save again and compute. Well, actually, we'll save this again and we'll say run. So that way, this file will have all the data. And the other one will just be the setup file. So we'll go ahead and compute.